right, we had some primary exposure factors. What were those?
KVP.
KVP and mass. Good. And Janelle, for mass, what can we break mass down into? What two exposure factors? Well, let's take a look at mass, right? It's 3 letters. What are the first 2 letters? MA, what is that? What do you think the A stands for in MA? Think back to your physics. Amperage, amperes, very good. So MA is your milliamperage, or milliamperes. And what does ampere, what does that unit describe? What does an ampere measure? Still asking you, Janelle? Current, electrical current, very good, right? So MA is current. Then what about the last part of mass, the S? Emily, what does the S stand for? Seconds, very good, right? So mass is 2 exposure factors combined. Your current, which is milliamperes, and your seconds, which is your exposure time. Great, so those 3 were the primary exposure factors. And then we begin to discuss some secondary exposure factors. Okay. So yes, one of them was focal spot. And what does focal spot affect? What about the image? What image property does focal spot affect? Great, focal spot affects the sharpness of the image, right? How blurry the edges of a structure will look. So if we have a bigger focal spot, what happens to our sharpness?
It decreases.
Yes, it becomes more blurry, it decreases. Very good. Okay. So in that case, why would we ever want to use a focal spot? Don't we want sharp, clear images?
We need a small one.
Too hot. Yes, heat. Right? So you need your focal spot, the smaller it becomes, the more concentrated the heat becomes. You can melt your target if the focal spot is too small and you have too much heat. So we do need a large enough focal spot to handle the heat. So for something like the abdomen, what focal spot would you use? Big or small?
Big.
Big. What about for a finger?
Small.
Small. What about for the foot?
Small.
Small. What about the chest?
Big.
Big. Good. Let's see.
But
Yes.
the focal spot, or the focal spot size, is that something that you can change, or is that already set in the tube, though?
So yes, that is something you can change yourself.
It's just the angle you can't change.
Correct. The angle you cannot change.
Okay.
And when we do change the focal spot size, exactly what are we doing inside the tube? What are we actually selecting when we choose the focal spot size?
The filament?
The filament. Very good. Because we have a dual focus filament, right? We have a dual focus tube. You have 2 filaments, one big for the big focal spot, one small for your small focal spot. Don't forget your filaments. They're going to pop back up with Miss Bonilla. And then we talked about magnification. Right? So with magnification, distance plays a role. So what kind of distance variables do we have, Samantha?
Let's see, distant variables.
Give me an example of a way we describe distance in X-ray.
SID, OID.
SID, OID, very good. SID and OID. There's a third one. Do you remember that?
SID, OID. Let me see how the SID, OID. And the other one. SID. Yeah, it's not.
SOD. SOD.
Source to, no, it's
Source
it's
to?
object distance.
Good.
Okay.
Source to object distance, SOD. Right, so we have SID, SOD, and OID. So SID, right, distance from the tube to the IR. OID, distance from the object to the IR. And SOD, distance from the tube to the object. Now, for magnification, which 2 variables do we use in the equation? What is the equation for that magnification?
SID divided by
Yes, it's SID over SOD. Just remember, SID over SOD. When you use the same letters, right, SID and SOD, only thing that's changing in the middle, and I comes before O, right? So SID over SOD. So that gives you your magnification factor. Great. And then we have this here, inverse square law and direct square law. With inverse square law, what information does this tell us?
As the distance increases, intensity increases.
So as the distance, let's say if the distance increases, what happens here to intensity? Decreases, goes down, right? So the farther we are from the IR, the fewer X-rays will reach the IR. Now, normally, we don't want less X-rays reaching the IR, correct? Normally, we want the same number of X-rays. So if we want to keep the number of X-rays the same, what do we call that? Maintenance. Yes, and we'll be using direct square law for that. Good. So we're trying to maintain intensity, right? At the IR, now we use direct square law. So if the distance increases, what needs to happen to the mass?
Increase.
It also needs to increase. Very good. Right, so make sure you're able to keep track of when to use which one. If we're talking about intensity, number of X-rays, right? How many X-rays reach the IR? Inverse square law. But if we're talking about what mass we should use to keep the intensity the same, now we're doing maintenance, right? Maintenance is direct square law. Good.
So if you increase for the direct, you increase what? For the direct?
So if we increase the distance, we increase the mass.
Okay, thank you.
So inverse square law, let's try it out. We've done this before, so it shouldn't be too bad. Right? We have our SID, it's changing from 40 to 72. What is our exposure going to be if it used to be 10 milligrams? What is our new exposure? Right? So what do we put here for intensity 1?
10.
Good, that's our 10 milligrams. Intensity 2? We don't know it yet. Distance 2? 72, good. And distance 1? 40, great job. So we plug these in. Okay. Went ahead and simplified d squared. So 72 squared is 5184. Right, 40 squared is 1600. So we have 10 over I2 equals 5184 over 1600. We can just cross multiply. And when we cross multiply, we should end up with 3.09 milligrams. Let's double check our work. Did the distance increase or decrease? Increase. If it increases, do we expect exposure to go up or down? Down, right? The farther away you are, right, the fewer X-rays reach it. Just think of a flashlight, right? The farther away the flashlight is, the less bright the light becomes. Same idea. So, did our exposure go down? It did. That means we did it correctly. Very good. Now, same distance, right? 40 inches to 72. But this time, we're not doing intensity anymore. What are we doing? Mass. What are we trying to do with this mass?
Keep it the same.
That's right. Maintain exposure. Keep exposure the same. So this is maintenance, which means which equation are we using now?
Direct square law.
Direct square law. Yes, very good. So we're maintaining, we're using direct square law. What is mass 1? 10. What is mass 2?
X.
Don't know yet. That's our x. Very good. What's our original distance? 40. And what's our second distance? 72. Good. Okay, once again, we put these into our equation. Notice, right? These are now flipped, right? Because this is direct square law now. And so once again, we have this, we have this. We do our cross multiplication. And this time, we end up with 32.4 mass. So let's think about it. Does this make sense? Did our distance increase or decrease? Increased. When our distance increased, earlier we said what happened to intensity? It went down, right? We put a flashlight away, it gets less bright, so the intensity went down. If we want more X-rays, right? If we want to bring the intensity back up, then what needs to happen to mass? Mass also needs to go up, right? If intensity goes down, we need to use mass to bring it back up. And so, is our mass bigger than the original? Is that what we expect? Yes. So when we are maintaining here, right? Bigger distance, we expect a higher mass to keep that same intensity.
So for maintenance, so the one
So we don't cross multiply?
So you'll cross multiply here and here. You'll cross multiply these two. This is just this here,
Right.
without the squares, right? So you go ahead and cross multiply this side and this side. And so when you cross multiply, right, you have this times this, right, this times this. And then, right?
I thought it was just across, like 10 times 16.
So setting up the equation, right, the ones are going to be on the
Right.
same side,
Uh-huh.
twos are on the same side. That's what makes it direct. But when you're solving it, right, you still need to cross multiply.
Gotcha, okay. That's right.
I know, you went from one math class to another math class.
Mhm.
Right, so notice how things change, right? Inverse square law, intensity went down as distance went up, right? Because it's inverse. Direct square law, mass went up when distance went up because it's direct. So inverse square law, they go in opposite directions. Direct square law, they go the same direction. Okay, so intensity changes by a certain factor, mass changes by that same factor, but in the opposite direction. Right? So here we divided by 3.24, here we multiply by 3.24. Yes?
Okay, so I know direct square law goes with maintenance. What was inverse square law? What did I know?
That goes with number of X-rays reaching the IR.
Oh, that's just trying to find out.
Right, so what's the dose at the intersection? And inverse square law, right? This is useful to us because this is what helps keep us safe, right? When you do portables, what did the text tell you to do? How far should you stand?
6 feet.
Right. You're standing 6 feet away, right? You're decreasing your dose using the inverse square law, right? As distance increases, dose decreases. If you want to be even safer, you stand even further back.
Some of those texts really don't care. They'll literally be standing right next to the two.
Well, that's
Testing.
yes, that's their choice.
Oh, and then they don't have the dosimeters on.
Okay, that's
Also their choice.
that's a bit more concerning.
That's a you problem, right?
That's a them. That's a them.
That's a them problem.
That's a.
Don't be that type.
No, I know. Like if it's like when they're doing multiple tests or multiple, they all put the shield. Because if we're gonna be in the room longer, I
I see.
So, Mr. Phung,
Yes.
like in Benzell, one of the unit have 4 beds. Like it's not even 6 feet apart. But when you do X-ray, the curtain is not going to protect the other patient.
So, in that case, right, you need to work with what you have. So, number 1, collimate, right? That way you have less of the primary beam there to create scatter. Okay. Number 2, remove anyone that can be removed. Right? So if there's any visiting family members there, right, don't just leave them there, right? Ask them to step outside the room just for a short moment when you do the X-rays. Okay? And then number 3, make as few exposures as possible. So do your best not to repeat so that you minimize, once again, the scatter to the nearby patients. Now, just keep in mind, right, the dose that the nearby patients are getting is only coming from leakage and scatter, not the primary beam. Okay. So the dose to them is considerably less than the dose to your actual patient in the first place. As long as they're not constantly exposed to those X-rays, then it should be okay. And as long as you're not doing like 3 chest X-rays every day for like 6 months and the same patient is there next to the patient 5 feet away, it should be okay. Yes, Samantha.
Hey, just on this topic, I was reading kind of something online. I'll read like radiology tech forums. Some people had said that even when they're doing portables, they're actually wearing lead. I don't know. I mean, obviously I haven't noticed that anywhere at Bentob. Anywhere have you worked? Have you seen that? Have you seen anybody doing that? Do you think that's overkill if you were doing portables?
That's a personal preference. Personally, I do think it's overkill. But it is personal preference. Some people just have different levels of risk tolerance than others. Personally, one reason I don't like to wear lead around patients is because it gives patients the wrong idea. It makes patients more scared than they need to be. Now, of course, I would normally show the patient. If not, and they request it, I'll educate them on why they can't be shorted for whatever procedure it is, like abdomen, right? But no, yeah, generally I do not wear lead on portables or on X-rays. Only in fluoral and OR cases because those are high dose areas. Portables and diagnostic are considered low dose. But yes, personal preference.
I'd love to see you weight training.
And it's heavy to wear.
Yeah.
It'll be heavy.
It is.
You're wearing it all day.
It would be fast as heck if you take it off though, if you're wearing it all day.
Like the rocket blades?
Yeah.
Okay. All right. Source SID, source to image receptor distance. Oh, I guess we didn't cover it last week or week before. We must have covered it last semester then. But let's talk about it again. Okay, SID. So, right, short SID, long SID. Right? Notice here with this short SID, when these photons come down, right? Look at this corner. This corner will cast a shadow all the way out here, right? This corner casts a shadow out here. So the size of this here looks bigger on the image. Right? You increase your SID, now this corner only shows up here and here, right? It looks a lot closer to the original size. So, right? Increasing the SID will decrease magnification, right? Small SID gives you more magnification. So this is just based due to the divergence of the beam, right? The fact that X-rays come out at this angle is spread out, divergence of the beam.
You said a small SID gives what?
Small SID, more magnification, more divergence. Okay, so we have some standard distances. Normally tubes would lock in somewhere like at 40 inches, 48 inches, 72 inches. If you do have OID, you do want a longer SID. For example, when you do your AP C-spine, what is your SID?
40.
40. When you do a lateral C-spine, what is your SID?
72.
72. But it's the same body part, it's the C-spine.
No.
Why do we have a longer SID on the lateral?
Because of the OID.
That's right, we have OID right here. The C-spine is right by the IR when you're AP. But on the lateral, now we have all the space due to the shoulder between the C-spine and the IR. So more OID means more SID is needed to reduce magnification. Okay, so OID, that's the distance from that object to the IR. If the OID increases, the intensity at the IR decreases. You know, increased divergence of the beam, fewer X-rays reach the IR. And we can even use this to help reduce scatter through something called the air gap technique. Okay, so for example, if I'm right up against the IR and there's scatter coming from my body, that scatter is going to go a very, very short distance and reach the IR, correct?
Mm-hmm.
But if I step away from the IR, now if scatter is coming out of my body, the scatter can go off at an angle and miss the IR, right? And so that is the air gap technique. By putting distance between the patient and the IR, some of that scatter is no longer going to go towards the IR. It's going to go off at a different angle and go off to the side, go past the IR instead. So that's one way to reduce scatter. However, what is the downside to this?
Spatial resolution.
Why is spatial resolution? What happens when you increase OID? That's right. So we have more magnification, right? So we have less scatter, but more magnification. So it's a trade-off, right? You're getting rid of one bad thing, which is scatter, but now you've got something else that's not so great, which is magnification. So you need to decide which one is more important at that moment. Okay? And because magnification does reduce spatial resolution. And then, just like we said earlier, with Samantha, we have SOD, source to object distance, right? So SID, right, your source to image distance, is equal to your SOD, source to object, and then OID, object to IR. By the way, does everyone have the PowerPoint? It should have been sent out 2 weeks ago. Can I move on?
Yes, sir.
So, just a diagram to demonstrate this, right? Source, IR, so that's our SID, right? Here's our object. So we've got the SOD, which is source to object, and then we have the OID, which is object to IR, right? So SID is just SOD plus OID. Right? SOD plus OID gives you your SID. Okay, and so here we have some more equations. Okay, magnification factor, MF. Okay, so you can call someone an MF, and you can be calling them a magnification factor. Okay, this is
Speaking my language, Mr. Phung.
SID over SOD. Okay, so just remember, SID over SOD, right? It's S here, it's D there, the only change is I on top, O on bottom, right? I comes before O, so SID over SOD. And then we also have this. Object size is image size divided by magnification factor.
Oh my God. Is ML.
Oz is MF, yes.
So you is an ML.
No, Oz is MF. I don't know who Oz is, right? It's like Dr. It's like a discount Dr. Oz, right?
Yeah.
Dr. Oz is OZ, this is Dr. OS.
To remember that, you know, you is an ML. Yeah.
Yes.
Oz is MF.
Yeah.
In order to be Oz, you have to be. You is.
However you can remember it.
Okay, Oz is.
But here, object size. So object size is the true size of the anatomical object, right? Image size is how big it looks on the image. So because there's magnification, the image looks bigger than the actual object. Does that make sense?
Yes.
So to find out the actual size of the object, we need to take that image size and divide by our magnification factor. So the image size looks bigger than it is. We need to divide by whatever's making it bigger, and that gives us our true size, object size. Right? So, for example, right, if I've got my hand here, right? My hand looks a lot bigger over there on the wall, right? So if I can measure the size of the shadow on the wall, I can divide by my magnification factor, and that'll tell me how big my hand actually is. And that's right, my hand gets blurry because of that magnification, right? We lose that resolution. Excuse me.
Are we getting sick, Mr. Phung?
I hope not.
I have a question.
Yes.
So, on the test, are you gonna give us like the image size, and we have to figure it out, or?
Right. So I could, for example, on an exam, give you SID, SOD, and ask for magnification factor. I could give you SID and OID, and you first need to calculate the SOD, and then give me the magnification factor.
Can you give us a worksheet? That's a lot.
I can give you a worksheet, yes.
Not for grade.
I also could
That was too
also
easy.
give you SID, SOD, and image size, right? So you need to calculate your magnification factor first, and then use it here to get your object size. Yes. That's a great question. We'll see how far we get today. So, if the SID is 72 inches and the SOD is 68 inches, what is the magnification factor? Once again, what is that equation?
Sit over side.
Good. Sit over solid. Great job. Good. So sit is 72. Right. Solid is 68. What is that?
1.06.
1.06. Did everyone else get 1.06? Sure. Okay. Yes, it is 1.06. Very good. Okay. This time, SID is 72 inches. OID is 8 inches. What is the magnification factor? So remember, SID is the biggest one. So to find the SOD, you need to subtract. Very good. So SID is SOD plus your OID.
72 is about 64.
72. So we need to subtract our 8. Good. So our SOD is 64. And then, once again, SID over SOD. 1.13. Is that what you got, Charles? Fancy?
No. 1.13.
Yes.
It's 72 over 64. What did you get for that one?
1.125.
1.125? Okay, so I just
So
rounded
you
up.
rounded up.
I just rounded it.
Oh, okay, never mind,
Okay, so do we see how we can kind of have this extra step sometimes in magnification?
Yes.
If you don't have the SOD, you need to calculate the SOD for yourself. No worries. And then we can go one step further and ask about how big that object is going to be, or how big the original object is. So here, if we're asking about how big an object appears, am I asking to calculate the object size or the image size?
Object.
Image size.
So how big it appears.
The object size.
This is image size.
Image, oh.
Right, the appearance is the image size. The actual size of the object here, this one is the object size. So,
So we're using
once again, right? We have OID. We need to get the SOD first. So SID minus OID should give us our SOD. So what is our SOD? Carla, what is our SOD going to be?
Sit minus side is 40.
4? Well, SID is 40. OID is 8. So what is the SOD? What is left over? Oh, 32, yes, very good, 32. Great. And then we have SID over SOD. Okay. So, Jay,
Yeah.
what is our magnification factor if our SOD is 32? Go ahead and use a calculator if you have it.
You're asking for a magnification factor?
What is our magnification factor? SOD is 32, the SID is 40. So there's SID over SOD for magnification factor first.
1.25?
Good, 1.25. So magnification factor has no units. Right? SID and SOD, those would have units of inches. And now the final equation that we need, it was object size is image size over magnification factor. So what is the object size? 4. What is the image size?
1.25.
Don't know yet. And what is MF? 1.25. Very good.
We say doing too much.
Will they ever give you object size and not image size?
That's possible.
Do you multiply it when you do one side?
That's right. You just multiply each side by 1.25. And so when you do that, you should get 4 times 1.25. And what does that give us? That's right. We should get 5.
Is 5 centimeters.
That's right. It is 5 centimeters. Right, so our original object size was 4 centimeters, right? But it looks like it's 5 centimeters on the actual image because of this 1.25 magnification factor. So it made the object look bigger than it really is.
So we get 3 points for this?
What is
on the
that?
exam? We get 3 points for this? Because there's 3 different steps.
Oh, like, yeah.
But
He's
it's,
gonna be
well, it's
worth
just
it.
one question.
Oh.
That's just one
One
question.
question.
Love it.
So you get 1 for 1
Not the MS.
Yeah.
I tried.
We appreciate you, Cindy.
Yes.
All right. So here, if the SID is 45 inches, okay, kind of a weird SID, but we'll deal with it. OID is 15 inches. What is the true size of an object that appears to be 12 centimeters? So appears to be 12 centimeters. What is this? The image size. Very good.
As it appears to be, right?
So let's see, Sindhu, what do you think the first thing we should do is?
So we need to find the SOD.
SOD. Great. How would you do that?
So 45 minus 15,
45 minus 15. Very good. And that gives us?
that's 25. No,
That's 25.
35, 30.
30. Yes. Very good. So our SOD is 30 inches. Okay. We've got our magnification formula here. So, Melanie, what is our magnification factor if the SID is 45 and the SOD is 30? Go ahead and divide that.
One.
1.5. Very good. So our MF is 1.5. And then finally, we have our object size equation. So Angelica, what is our final object size here?
So it's gonna be 12 divided by 1.5.
Very good. 12 divided by 1.5.
8 with the 12 goes with the IS. Not OS.
Correct. So this appears to be. So the appearance tells you that it's image size.
So when it says appears to be, it's always going to be image size.
Right. The size on the image, the size on the monitor, how big it looks like.
So 12 divided by 1.5.
And that is 8. Very good. So it looks like it's 12 centimeters on your image, but in reality it is only 8 centimeters in the patient. Right? The magnification is what makes it look bigger than it really is. Right? So you see something on the monitor, oh, look at this mass. Let me measure this mass. It's a 12 centimeter mass.
Yep.
Okay, but no, right? There's magnification. Right, so in this case, it was actually only an 8 centimeter mass. Does that make sense?
Yeah.
Okay.
Yeah, it looks easy now. You're gonna put it in the
So, right, if an object is 15 centimeters in reality, but it looks like 18 centimeters on the image, how much magnification was there? Well, we just find our normal magnification factor. Right, so we've got object size, bless you, which is 15, image size, which is 18. Right? We'll solve for our magnification factor here. If we want to make this easy, imagine this is 15 over 1, and you can cross multiply. Okay. And that will give you a magnification factor of 1.2. I put in those extra 0 here just to make it more obvious, because if you're trying to turn this into a percentage, right? To turn this into a percentage, you take off the 1, and then you multiply this by 100. So you move this decimal point over 2 places. And so that gives us 20%. So a magnification factor of 1.2 means that it looks 20% bigger than it normally is. Right? Magnification of 1.5, 50% bigger than it really is. Magnification factor of 2, 100% bigger than it really is. Right? But hopefully you never run into a magnification of 100%. Right? 100%, because that means you got a ton of OID. It means your picture looks twice as big as it really does. Your finger looks like the size of a forearm, right? So hopefully you never have huge magnification factors. Try and keep them small. Okay. Final notes about magnification. Notice how each variable affects magnification. Right? If you increase the SID, that decreases the magnification. If you increase the OID, sorry, if you increase the SOD, that decreases magnification. And if you increase OID, that increases magnification. So SID and SOD, increasing them decreases magnification. Right? But OID is the odd one out. Increasing the OID increases magnification. And as magnification goes up, spatial resolution goes down. Okay, any questions about magnification? That's pretty much all you need to know about magnification. SID, SOD, OID, magnification factor, image size, object size. Okay. In that case, it is currently 1:13. Let's take a 10-minute break. Please be back at 1:23. If you'd like, you can join me for some stretching exercises. Otherwise, feel free to use the restroom. Elongation. So the shadow of the part will look longer than normal. Okay. In addition, this may slightly decrease exposure to part of the IR because you are going to have an increase in SID. And I'm sure some of you have noticed that in lab, right? You throw on the angle, you look at your SID, and now the SID is longer than originally. Right? So throwing on an angle increases your SID. On the other hand, if the body part is angled, so if it's not laying flat on the IR, but it's like lifted up, now you have foreshortening. Very good. So, an example of this, when you did your partial flexion elbows, right? Your trauma elbow, partial flexion, right? So you have to do one like this and one like this, right? Mm-hmm. When you do this, you'll notice that whichever arm is up is going to end up looking foreshortened. The shadow looks a lot shorter compared to the other arm. That's why we need to do two pictures, right? One where the humerus is flat, so that looks the true size. And then one where the forearm is flat, so the forearm looks the true size. Right? We can't just do this because this will look foreshortened. We can't just do this because this would look foreshortened. And we definitely cannot do this because both of them will look foreshortened, right? So that's why you do one with the forearm flat, one with the humerus flat.
What is that for?
That was the partial flexion elbow for the trauma.
They both.
So if you angle the IR or the 2, you'll have elongation. But if you angle the body part, you have foreshortening. Right, so if the equipment is angled, elongation. If the patient is angled, that's foreshortening. Are we okay to move on? Okay, next up, grids. We're not going to go too far into grids this chapter. Grids will be next chapter, I believe. Okay. But the purpose of grids is to reduce the scatter which reaches the IR. Okay. That's the key word here, reaches the IR. Do grids reduce the amount of scatter produced?
No.
No. What have we talked about which reduces the amount of scatter produced?
Like filtration.
Not filtration.
Small, the focal spot.
Collimation. Collimation is the thing we talked about which reduces the production of scatter, right? You reduce the area the X-rays cover, so there's going to be less scatter produced. Grids only help to reduce the scatter that hits the IR. The same amount of scatter is being made, but less of it is actually reaching the image receptor. So when do we use a grid? Usually when the anatomic part is thicker than 4 inches. So finger, right? No, doesn't need a grid. How big is 4 inches? About this much. Right? Hand doesn't need a grid. Okay. Wrist doesn't need a grid. Forearm doesn't need a grid. Elbow doesn't need a grid. But shoulder? Yeah, you want a grid for the shoulder, don't you? Okay. Down here, lower extremities, right? Foot, ankle, tibia, probably don't need a grid. But you get up to the knee, you get up to the femur, you get up to the hips, right? Thick anatomy. Now you're going to want to use the grid. Now, here is the thing about grids. Grids don't only reduce scatter. Grids also reduce the amount of transmitted radiation. Right? So they also absorb transmitted radiation. So the quantity of X-rays, the number of X-rays reaching the IR goes down when you use a grid. The intensity at the IR goes down when you use a grid. Do we want intensity to go down? No. No, we want it to stay the same, don't we? So we want to maintain intensity, but using a grid decreases the intensity. So what factor do you think we're going to change to bring it back up? I heard mass. Mass? Anyone else? Mass? So,
Increasing KVP, decreasing mass?
could you increase KVP? Perhaps. But what did we say is our controlling factor for quantity?
Mass.
It is mass. Right, so the first thing you want to change is mass. So yes, mass is what we are adjusting when we add or remove the grid. So here on the left side, we have grid ratios. Here on the right side, you have grid conversion factors. Have we seen this chart before? I don't remember if I went over this in semester 1. We have not. First time seeing this chart. Okay, guess what I'm going to ask you to do? Yes, please memorize this chart. You already knew it. So you need to know the grid conversion factor for every single one of these grid ratios. If I tell you what is the GCF for a grid ratio of an 8:1 grid, you should immediately say 4. If I ask you what is the grid conversion factor for a 12:1 grid, you should immediately say 5. Bless you. If I ask you the grid conversion factor of 2 goes to which grid, you should immediately say 5:1. right? You need to know these numbers. You have to know it backwards and forwards, yes.
Why is 10 and 12 the same 5?
So they absorb about the same amount of radiation.
So you won't ask like, girl came back from break 5 and then give us 10 and 12?
No, I wouldn't do that to you. Yes, welcome back from spring break.
Any of us were ready to come back?
So, please do. Please take as many pictures as you need.
You sent this PowerPoint though.
I did send a PowerPoint, yes. Great question.
I was just
So,
asking myself.
Grid
I got no
ratio
storage.
tells you, so I don't want to go too deep into this yet because we'll go more into this next chapter. Grid ratio basically tells you how efficient the grid is. The higher the grid ratio, the more stuff there is that's getting rid of scatter. Right? But the more stuff that's there getting rid of scatter, the more stuff that's there also getting rid of normal X-rays. And so we lose more intensity down here, and we need more mass. So the grid conversion factor tells us how much to change our mass by. So we are going to use this equation over here. This is our maintenance equation when using a grid. We have mass on one side, we have the grid conversion factors on the other. This is directly related. So mass 1 goes to GCF1, mass 2 goes to GCF2. So let's take a look at this in action. If an abdominal X-ray uses exposure factors of 80 kVp and 32 mass with an 8:1 grid ratio, what mass should be used if the grid is removed? So
that's the original grid.
All right,
Grid
so-
1 is 8.4. So that's grid 1, right?
Okay,
8 to 1.
so, all right, so yes, let's take a look at grid 1 first, right?
Okay.
We're starting with an 8:1 grid. What is the grid conversion factor?
4.
4, great. And we're going to a removed grid. So no grid,
Yeah.
which is 1. No grid.
Oh, okay.
So we're going from 8:1, which is 4, down to no grid, which is 1.
So it's going to be
So
8,
then
right?
you just divide
It's just
mass
8.
by 4, or?
Yeah,
So,
it's just 8.
yes,
So 4.
we throw it into our equation here, right?
And it's just 8.
And then, but yes, basically we're going to divide by 4.
Okay, thank you.
And we end up with 8 mass. So we're trying to find our new mass without the grid. Right? So because we're taking away the grid, there's nothing absorbing the X-rays anymore. So we don't need as many X-rays anymore. So direct, right? So this is directly related. If the GCF goes down, the mass goes down. If the GCF goes up, the mass goes up. Directly related. Okay. So, right? Let's say you're doing a portable X-ray. You go to the patient, you're like, all right, 80 kVp, 32 mass. You get it over, you get your cassette, and you're like, oh shoot, no one put a grid inside here.
Oh, shoot.
Right? Someone forgot to replace the grid. I only have the IR, I do not have a grid.
You just blast
I need to
it.
change my mass now. I need to change my mass. What do I change my mass to? This is how you would do it.
I think the...
Bait.
If it's a portable, it will.
Oh, portable.
If it's a portable, it will. Right, so a lot of this is very useful for portable because you have grid getting put on or taken off depending on your patient. And so this really helps you figure out what kind of techniques to use. You don't need to be so accurate, right? But as long as you're in range, you'll be a lot better.
The good thing is that the machines tell you what grid to put.
It does, but what happens if someone forgot to put the grid back in the machine?
Dun, dun, dun.
That's right. Who did this? And then you're like, no, 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 that's a cell. You can't do that. That's a cell.
It's a song.
He's gonna call you.
Reagan said, I'm done with this.
Yes,
Grid reduces the amount of X-rays passing through.
correct.
So if there's no grid, then we'll be decreasing mass.
Correct. Okay, let's try this again.
If it's
All right.
red, you decrease it.
Shoulder X-ray. Let's say we've got a shoulder X-ray. We're using 75 kVp, 8 mass, and a 5-to-1 grid. Right? But now, instead of a 5-to-1, we end up using a 12-to-1 grid. Maybe they upgraded the grid for the machine, and now we have a 12-to-1 grid instead. What should our new mass be?
8
So,
Is that 2?
2, yes.
I think it's 2.
2
Yes, and
over
2.
5.
2, and that's 5.
Good. And then 12-to-1 is what, guys?
5.
5. Very good.
7.
So, we've got our equation here.
Mass 1 is 8
Last one is 8
over x
over x.
equals 2 over 5.
Very good.
So I scatter
Perfect. And then we go ahead and solve this. And we go through everything. We should end up with 20 mass. Still have 23 minutes.
It would be nice if we can finish a little bit just.
Okay. Fine.
I will take that into consideration.
Oh, never mind. He's like, yeah.
Next up, beam restriction. Right, so collimation, right? Beam restriction is collimation. So if we have poor collimation, right? If we aren't collimating properly, that means we're going to have more X-ray interactions, which gives us more scatter and lower contrast in our image. So we want to increase our collimation. We want to make the light field smaller so we get a higher quality image, right? Less scatter, and so less fogging, higher contrast. Now, yes, if you collimate, right, you have less X-rays reaching the IR, so you may need to raise mass very slightly to compensate.
Okay, wait. One question real fast. So collimation, okay, whatever, increasing your collimation will give less scatter reaching the eye. But what about the grid? That's why I get confused just a little bit.
Yes, so your collimation helps reduce scatter production. Grid reduces scatter that reaches the IR after the production. Ideally, you want to use both. You're going to reduce scatter by having good collimation and a grid. Primary and secondary.
Increasing collimations for me, for the first thing that comes up is like opening, you know? But
That's
I
right.
know it's not.
That's right. So try to get you guys ready for this all the way back in summer 1. I already warned you, right? Collimation is confusing, right? Increased collimation means make it smaller. Right? I'll try and tell you, like open it up or close it instead. But yes, right? That is how the wording goes, because collimation is about restricting. So if you increase the number of restrictions, right, the stuff you can do is smaller.
What about when they say close call?
So when they say close it up, right, then that means to make it increasing collimation.
So increase it means
So,
Close
so increasing is not about the size.
Are you making it smaller or bigger?
So just think of the word collimation as restrictions.
You know how
Right? Collimation is restriction.
So it's like me now, like putting it all
Right. Open and close collimation is like a door or a window, right? You open it, you close it, right? Nice and simple. But if we say increase or decrease, right? Now we're saying we're increasing the restrictions. If we're increasing restrictions, then that means things are going to get smaller. If we decrease restrictions, then things are going to get bigger. It's confusing. I agree. It's just something that we need to work with, unfortunately. Okay, generators.
No.
Decreasing collimation increases scatter.
Decreasing collimation increases scatter.
Thank you. All right.
Correct. Okay, so generators, you're going to learn about, or talk about these with Ms. Bonilla as well. But real quick, single phase, these are your most basic generators. So they produce less exposure. You need higher techniques to compensate. 3-phase produce higher exposures. High frequency produces the highest exposure. Okay. Yeah, I'm not going to go too deep into generators right now. I'll leave that for Ms. Bonilla. Okay. Keep in mind, each X-ray machine and facility has its own set of optimal exposure techniques. Right, so this GE machine is going to be slightly different from this Siemens machine, which is slightly different from this Philips machine, which is slightly different from this Carestream machine. Okay, so each machine has its own optimal techniques, which means each machine has its own exposure technique chart. Each machine should have a chart that tells you these are the best values to use for each kind of exposure. So it looks something like this. You have your body part here, right? You have even the part thickness, how thick the body part is over here, right? You have the kind of exam, right? PA chest or lateral chest, right? Of course, the thickness is going to be different for them, right? You have your SIDs, and then you have your KVPs, and then you have your masses, right? And then it's even divided by patient habitus, right? Small patient, medium patient, large patient. What mass should you be using? So this is an exposure technique chart. So you see a patient, you're like, all right, patient looks like this size. I'm going to be using this KVP and this mass for that patient to get an optimal image. Now, once again, exposure technique chart, honestly, not so important anymore. These were pretty much your Bible back in the film screen days. Right? This was your holy book back in the film screen days. Yes, this would tell you what to do to get that optimal image within your dynamic range. But nowadays, with digital, even if you're off, what happens? Automatic rescaling. Even if your techniques are off, it still rescales your image, pre-processes it to look proper. Yes, Jay?
So, is the measured portion habitus?
So measure is going to be part thickness. So you have your caliper and you measure how big your patient is.
You showed us how to use that like in first semester, right?
I don't think we went over the chart in first semester.
No, the caliper.
Like caliper.
Did you show us that or something like that? I mean, I know you showed
Yes.
us.
When we were doing extremities, we used.
So I showed it for the knee. So once we're with me, I put it out for the knee.
Yeah. Oh yeah, you did put it for us. I just can't remember what semester it was.
So yes, that was last semester. Okay, and then if you remember our emission spectrums, tells us exactly the same thing we just discussed. Right? So, right, the number of X-rays produced is higher as the generator is better. And the quality, right, is also slightly better with better generators. And once again, you'll learn exactly why this is with Miss Blumier. Filtration, another old friend of ours. Okay, so all X-ray tubes that are going to be shooting above 70 kVp should have a minimum of 2.5 millimeters aluminum filtration. Right, so if you go to your dentist, their X-ray tubes aren't going to be as strong, they're going to have less filtration. But for diagnostic radiography, we routinely shoot over 70, right? Chests, abdomens, pelvis. So minimum 2.5 millimeters filtration. And this is total filtration, right? Total filtration, that includes our inherent and our added. So why do we need filtration?
To remove the low energy X-rays.
To remove our low energy photons. Very good. Right? Low energy photons don't contribute to the image, they only add to patient dose. So we want to get rid of them to minimize patient dose. Right? So this decreases the quantity, but increases the quality of our X-ray beam. We have more high energy photons compared to low energy now. Okay? So keep in mind, right? Higher average energy, right? Higher quality means more scattered and lower contrast. Okay? But generally speaking, right, filtration should not vary by very much. Filtration is set in the machine, you're really not going to change it. So whatever it is, it is. Right? It's already installed. That's right, there is a third type.
This is tube filtration.
Correct, so this is tube filtration. But the third type of filtration, right? And once again, you can see, right, as filtration increases, number goes down, energy goes up. The other type of filtration was compensating filtration. So this isn't here to remove low energy X-rays, right? That's right, this gives us a better quality image. For example, look at the shoulder over here, right? What is this here? Scapula. Great, and then what's this over here? Humerus, and is this an internal or external rotation shoulder? Internal. Why do you think it's internal?
Because the joint space is closed.
The joint space is closed?
Yeah, isn't it like...
It's still closed no matter what. You only open it up with the gray sheet?
It's the lesser.
That's right, we're supposed to check the trochanters, right? If this is external, greater trochanters in profile. If it's internal, then lesser trochanters in profile. Wait, where's the greater trochanter?
Is it true?
Or sorry, tubercle. Thank you, tubercle. Tubercle.
That's why.
Yeah, I got myself mixed up. But yes, where's the tubercle? You don't see it. It's burnt out, right? Too many X-rays blasted the humeral head. You can't see it anymore. So we use a compensating filter. So you see it's thick over here to help absorb the X-rays. And now you can properly see the greater tubercle there.
Anytime you say blasting with X-rays, I
Yes.
think of like, well, you gotta blow them up.
Yes. Yeah, think of it like a mafia movie, like pop, 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 right? You're blasting that part with X-rays.
Yeah, that's Wait, but I've never seen one of those. Like, are we ever gonna get
So they're not so common anymore. Once again, it's more of the film screen days. Nowadays, with digital, it's able to process our images better. But just in case you happen to see one of those, now you know what it is. Okay, so because we are adding in extra thickness with the compensating filter, sometimes you need to adjust mass just slightly higher, right, to make everything nice and even. Okay, and remember, when mass goes up, so does patient dose.
So if we were not using compensating filtration, then we decrease it.
Correct. That's what I would recommend.
I'm still gonna
Well, my phone's open up until 6 p.m. Okay. Well, as long as you don't change your number, right? If I see it's Emily calling me, then that's fine. But if it's just strange random number, I'm just going to leave it to voicemail.
Keep calling. Keep going.
Or you can text me, right? Okay. Body habitus.
No, you don't answer 6 hours later.
Body habitus, part thickness, subject contrast. Right, so now these are things that are related to the patient themselves. Body habitus, 4 types. Okay, summer 1 semester, let's go. What are the 4 types of body habitus? Samantha.
Okay, stenic, hyperstenic,
Stenic, hyperstenic,
hypostenic,
hypostenic,
and astenic.
astenic. Very good. Sindhu, most common type.
Stenic.
Stenic, great. Jamaica, least common type.
Mr. Phung.
Damn. You, aesthetic.
Me, astenic, all right, very good. Nope, actually it's hyperstenic. Oh.
Excuse me. Oh, hyperstenic. Me?
Yes.
So it's not you.
Okay.
If the question was like the most common in like a region, would the answer be different? Like let's say
Possibly,
like,
but we wouldn't teach that.
you wouldn't teach that.
No, we're just going for national group. And really, I mean, it shouldn't change too much by nation because this is about body type, right? It's not about soft tissue or anything like that. This is about body structure.
Oh,
Right.
I see.
So even, right, so I suddenly go and like, I go out and I binge eat for the next 2 years, right? And I come back and I'm like this, right? Right? That doesn't mean I'm not hyperstenic or asthenic still, right? Because my body structure, right, my bone structure, the way my lungs are shaped, right, that's all still going to be the same, even if I put on a whole bunch of soft tissue, right? So remember, body habitus isn't just about soft tissue, right? It's about the overall body structure.
So you would make you would make exposure changes like if your patient was hypersthenic when you thought they were asthenic or sthenic rather. You would make the exposure change then, like when they're like their bones are that much bigger, or like how are you able to tell that?
No, I mean,
Probably not when you see
so alright, generally speaking, right, you're not going to see that, right? Asthenic is going to be like thin and narrow, right? Hypersthenic is going to be the large, stocky, right? Wide-shouldered type of body. Okay. So, generally speaking, right? And once again, all these are general rules, right? Use your common sense, adjust as you need to. But asthenic will require lower exposure techniques. Hypersthenic will require a higher exposure technique. And this kind of goes into part thickness, because thicker parts require more mass, thinner parts require less mass. It makes sense, right? If there's less stuff for the x-rays to go through, you don't need as many x-rays. Now, remember that thickness follows the concept of half-value layer. Another old friend. So, remember, with each half-value layer, we decreased the intensity of the x-rays reaching the IR by a factor of 2. So now we see, right, we're decreasing the intensity. Normally, we want to keep the intensity the same. So what would we need to do to change this? Increase the mass, right? Anytime we see decreased intensity, we're going to want to increase the mass. Whoops. So every time the part increases about 4 to 5 centimeters, so that's about 1.5 to 2 inches in thickness, the intensity is going down. So we need to increase the mass. We're going to double the mass. Right? So if you have a technique for 10 centimeters, and your next patient is 14 centimeters, what do you do with the mass? You double it. Right? So 10 centimeter, you use 5 mass. Okay, 14 centimeters, I'll use 10 mass. If they go up another 4, right? Now it's 18 centimeters. All right, I'll double that again from 10 to 20 mass. And it works the opposite way as well. Although, of course, so yeah, back in the day, you'd put the caliper and be like, right? But now you can just eyeball it. It's not as critical. All right, so imagine we've got a hip X-ray, ABKVP 20 mass. Okay, hip is 20 centimeters thick. Next patient, you measure the hip, 24 centimeters. What do you think needs to happen to our technique? Good. That's right. It went up by 4 centimeters, so we just times the mass by 2. Perfect. All right. This time we've got a hip that's 28 centimeters. Right? It's 4 and then 4 again. So we need to do this twice. What technique are we going to use?
20 times 4.
That sounds high, yes.
Times 2, and then that times 2.
That's right. So we times 2 one time, which is 40. 8. Times 2 a second time. So yes, we would actually use 80 kVp mass. It does. But if you've got a really large patient, sometimes that's what you end up using. Okay. Now, okay, remember we talked about subject contrast before, right? It's the contrast, right, the inbuilt contrast of the patient, right, of the different organs, of the different tissues. Okay. Remember, right, contrast, right, depends on subject contrast, and then we also, as thickness of the part increases, we have more scatter as well. Right, so scatter is going to reduce the subject contrast. Right, subject contrast is what we want to see. Scatter will reduce our subject contrast. Okay. So, for example, if we have tissues like ear, soft tissue, bone, right? Ear and bone, right? Big differences. We're going to have high subject contrast here. But in the abdomen, if you're looking at things that are all kind of similar, right? Liver, kidney, gallbladder, then those have low subject contrast, small differences between each other. Okay? So subject contrast is what we want to see. Scatter keeps us from seeing our subject contrast. It fogs it, right? It kind of makes it all gray. Okay, radiation protection. So we can adjust our KVP and mass to help protect the patient as far as radiation goes. Which of these two, KVP or mass, is most responsible for patient dose? Mass, right? Mass is our main controlling factor for patient dose. So if we want less dose, we're going to drop the mass. But to compensate, what needs to happen?
Increase KVP.
Increase KVP. Very good. 15% rule. So use the highest KVP and lowest mass possible while still having proper contrast and avoiding quantum noise. Right? Because if you drop your mass too low, that's when you run into that quantum noise. And if your KVP is too high, you're going to lower your contrast. Okay. Beam restriction, collimation, right? Huge aspect of radiation protection. Collimate to the size of your IR, collimate to the size of the part. Right? Normally in test out, I'm pretty lenient with collimation, but if you've been with me, you do know that one of the things I'll take points off for in terms of collimation is if I see light beyond your cassette. But if you're 10 by 12 and you're giving me 11 by 13, you are losing that 5 points because you did not collimate to your IR.
You took 10 points off.
Well, it was 10 points. Really?
Yeah.
I swear the rubric only says 5.
Well, you took 10.
Well, you did
We'll see.
2 things.
All right. Grid selection. Remember, right, if we use a really powerful grid, like a 16:1 grid, that is a high GCF, which means we need a lot more mass in that case. And mass is patient dose. So we want to use the lowest grid possible to give us an acceptable level of scatter. Right? Some scatter, that's okay, it's acceptable. But that way we minimize patient dose. We don't want to use too strong of a grid if we don't need to. Right? And finally, right, even though the computer can pre-process, it can do automatic rescaling, don't just choose random exposure techniques and fire it at the patient. Right? You can't just be like, all right, I don't know what to use for a chest or an abdomen. All right, abdomen, Monsi, okay, let's go 80 kVp, 100 mass. I'm sure it'll end up fine. Right? And then you get the image and like, oh yeah, see, image looks perfect. Like, well, yeah, your image looks perfect because the computer rescaled it for you. Right? But you should have used a more proper mass, right? Something like 20 or 25. And finally, we have 2 charts here. These charts are the exact same as the charts in the back of this chapter. So chart number 1, you have primary beam, you have remnant, right, your exit beam. And it tells you what effect each exposure factor has on the primary beam and the remnant beam. Right? Notice, for example, that beam restriction, right, is going to affect, right, primary beam, it's going to affect exit beam. But something like grid has no effect on the primary beam. Why not?
It's in there.
It's after.
That's right, the grid's on the IR. The grid comes after the patient. Right? The grid cannot affect the primary beam. It can only affect the exit beam because it's between the patient and the IR. And then also here, you have exposure factors without compensation. So if we do not adjust our exposure factors, right? If we do not try and compensate, what happens? If we increase mass, right? We're going to have higher exposure. Notice we're not compensating for exposure here, right? If we increase SID, right? We have less exposure, right? I'm not compensating for it. This is just what happens without compensation.
We come up with compensation filters? No?
Just, I'm not trying to maintain anything. Right, so if I change these and nothing else, if the only thing I change is angle or filtration or KVP, right? This is what's going to happen. This is the only thing I change. Notice, however, there's one column that is not changing.
The brightness.
Oh, brightness.
Brightness does not change no matter what you do to these factors. Why do you think that is?
That's just the computer.
Because of the computer, which does
Reschedule.
pre-processing, specifically
Auto rescaling.
automatic rescaling, right? So because the computer automatically pre-processes your image, the brightness will usually end up about the same when you see it. You can't use brightness to judge these factors. Does that make sense? Right? Back in the film screen days, yes, this would change. In the digital era, right, brightness will not really change on your monitor. Okay, and that is it. That is the end of the chapter. Yes.
Question on that last, this one, okay,
Yes.
with the exposure factor, you said if that is the only thing that we're changing,
Correct.
the rest.
So this is the effect you would see.
Oh, that's what. Okay.
So I'm only changing KVP. You look at this row, and those are the things that are going to happen.
Can you go back to, I think it was like slide 30 something?
Remember the topic?
Just like go over the.
So you don't have to print it out.
It was on vibration or still
Does that mean his test is on Friday?
Maybe a bit earlier.
He didn't say anything else.
Oh yeah, actually yeah, that would be great. I think it was.
Yeah, I have it.
I want to say. Oh yeah, my fault. 13.
13?
Yeah. Because no, never mind. Whatever. It was along with my question first.
Sorry, let me put you on hold just for a moment. All right, everyone, we are done with PRE2 for today. You are now in study hall. Okay, please do not forget that you do have no cards due this week. In addition, I do have worksheets for you here, so if you have to pass this down, please.
Mr. Phung, does that mean your test is on Friday?
So tomorrow, or yes, so Wednesday will be review. The test will be on Friday.
One more for. Get one for
So this one here is going to be due on Wednesday. We are going to discuss this worksheet on Wednesday. Jay, did you ever figure out which slide it was? What a question?
No, I guess I thought I saw an image on